sees PL, as I just mentioned. As a function of temperature, we go down to 1.6 Kelvin, and magnetic fields. So we can apply, we've been talking about lots of inherent magnetic fields, but in this case, we're applying a magnetic field from 0 to 9 Tesla. And then uniquely, we can apply that field either parallel or perpendicular to the sample. And those two geometries are called Faraday and Voigt. Now, we've heard a lot about Faraday today, but I'm going to comment just a quick second about what that means in our case. So here, I'm so sorry. Let me get my pointer. Okay, here, our objective, so the way that we focus the light is actually within our magnetic field. And that, when we're in this geometry called the Faraday geometry, where the sample is perpendicular to the field, the objective itself, of course, composed of lenses, can actually rotate the light. And that is, of course, called the Faraday effect. And we have to correct for that. And I'm going to talk about that in just a second. Another geometry that we use often is called the Voigt geometry, where we stand up our sample, we remove the objective, and we use a small mirror lens combination. Now, in the Voigt geometry, we have a larger spot. It's on the order of 10 microns. Of course, it's wave dependent. In the Faraday, so it is diffraction limited. And then just to comment about some of the other attributes of this setup, we do are able to see low frequency phonons or magnons, and that we go down to approximately 7 wave numbers. That is dependent on the sample, and I hate to say the phase of the moon, but a little bit of that, just to be honest. So that gives us down to about 1 MeV. Again, very nice overlap with our neutron and terahertz colleagues. That is, we're able to do that because we're using a triple grating spectrometer. Nowadays, many people use Bragg filters to enable low frequency work. Because we use multiple wavelengths throughout the visible, that does become a little price prohibitive. So we use the triple grating instrument. Now, that does mean that affects our signal to noise, of course. We do have full polarization control, and honestly, that is kind of the meat of the talk. So we're going to talk about in just a second. I do want to tell you about our device transport is now up and working. So we have 10 contacts actually down to our sample. So we can actually run a live device. I'm going to show you a little snapshot of the progress we've made on that. And we can do spatial mapping, which of course is quite important, particularly with these 2D materials. So yes, polarization is really important. And again, because these meetings, these small meetings are always great, we're looking for exciting samples. Of course, if they're chiral, that's great too. But honestly, if not, if you have some samples that you think this kind of measurement capability could bring new insight to, please reach out. Okay, just a couple examples of where this magneto-Raman capability really is highlighted, and particularly with magnons. Of course, we heard a lot about magnons in the previous theoretical talk. Here are just some examples of what they look like experimentally. Mainly, my group deals with 2D magnetic materials, but we do a variety of them. I just want to give you a little context on the signal to noise talking about. This example is in iron PS3, and it is a small feature that was once in a previous paper characterized as a phonon. And when we applied our magnetic field, we were able to see that, in fact, it split quite nicely up to 9 Tesla. And in fact, that mode is a magnon. What's exciting is it was 5 years ago this month, I think, where there was another SPICE sponsored meeting, and it was all during COVID, and everyone was quite frustrated. And we actually gave a nice talk about the details of this work. I went to these other examples, but again, having this capability of both field, temperature, and ability to change the orientation of the field to the sample really gives us a nice measurement platform. A more recent example is actually in cobalt titanate. And I think this was mentioned a couple days ago in one of the talks. Here, what I'm showing is two of the magnons that we observed. Please note the energy scale here is an MEV and Raman shift, but you can see we are seeing features far below the, down to approximately 1 MeV as a function of field. And these two magnons, interestingly, actually cross at higher fields, and we were able to collaborate with a group in Grenoble to really show that. Another example that's not published, I just want to share because it gives a good context for the stability of the instrument that's required. This example is MNTE2. And over here, we have magnetic field along X and Raman shift along Y. At zero field, we actually see two magnons, one at about 20, one just shy of 30 wave number shift. But as we apply a magnetic field, what you can see, hopefully, and it's quite faint, can you see that this particular magnon splits into 3 different features at 9 Tesla? I bring this example to you, and this is unpublished work, because I'm not sure if you can see the counts per second over here. But these measurements took 3 days to acquire. And so the nice thing about this system is that we have a feature, a magnon, that does not respond to field at all. And it really shows the stability of the instrument, and that we're really excited about. Oh, and then lastly, I just wanted to say, in our second paper on the cobalt titanate, we were actually able to observe this Zeeman splitting of the E phonon with applied field. And that's actually interacting with some spin-on other features from that also happen within the field. And that paper is quite new. And I'd be happy to chat with someone offline about that work as well. And then lastly, on these examples, I just want to share again that our device transport is working. So we can obtain magneto-Raman and magneto-transport simultaneously. On the left here, we have an example of graphene. And what we're plotting here is the Raman shift of the G peak in graphene. And what we can see with applied magnetic field, again plotted here in Y, is an avoided crossing. That avoided crossing has been observed before. Again, a great French group was able to do this work. And they were able to see a magnetophonon resonance. And that resonance is with the Landau level coming from the quantum Hall. When in this particular device, we are able to apply and measure the full conductance or resistance in the sample, and you see the quantized plateaus in this case. When the spacing between the Landau levels is the same energy as the G mode in the Raman, you see this avoided crossing. And so here we're doing those measurements simultaneously. And what's kind of exciting, particularly as a spectroscopist, to be able to collect a quantum Hall fan diagram within our instrument is pretty. But just to be clear, we're new to the whole electronics area. But what we see is this ability is going to help us actually in measuring and doing new experiments on the chiral phonons going forward. So let's get back to this. Polarization is critical for our measurements to actually be valid. And that is, of course, because the Faraday rotation that I mentioned due to our objective being in the magnetic field. So to correct for that, just want to point out quickly here that we don't use fibers anywhere in this system. That's, of course, very important for polarization, but it also is a demand from having multiple wavelengths of light, depending on what experiment we're doing. So you will see all free space optics in this experiment. So to correct for the Faraday rotation, we have to do that as a function of wavelength and as a function of temperature. So we run test calibrations. Of course, we're at NIST, and so doing calibrations is really an important part of our day or life. So we make these tables, again, as a function of wavelength and temperature. In this case, I'm just showing a couple temperatures. This is 5K and 150. And I bring this up because there is more than one paper in the literature where people have used a similar instrument without doing this Faraday rotation, and it can lead you to believe there is quite colossal polarization effects from things. So again, this Faraday correction in this case to do with the objective and not the sample is really important. The instrument. So that correction, what we were using, of course, is we have 4 polarization optics, two polarizers, both on the incoming and the scattered light, as well as 2 half-wave plates, one coming when the light is coming into the sample, and then one on the Raman scattered arm. And those 2 optics, the 2 half-wave plates, are actually on rotators. You're able to control and do a full rotation on those, and they allow us to do these sort of 2D polarization maps, which I'll show you pictures of. These 2 optics give us, of course, the angle-resolved Raman. If we change out the half-wave plate on the entrance, we can, of course, do Helicity-Resolved Raman, and of course that has led us a bit into this community of looking at phonons or magnons or excitations that have a handedness to them. So while I've given you lots of details about this home-built instrument, I want to point out in our lab, we also have what I would call very standard instrument. This one is a Hariba instrument, more of a store-bought, and so this allows us, when we're thinking about polarization and the complications that we have on the other instrument, to look at this setup. Now, of note, in our home-built instrument, we don't use an edge filter, again, because we have those multiple wavelengths. In this case, we have edge filters for all the colors that we have on this instrument. It's 4 in the case, but this is also how most people are collecting their Raman data. And what we do, both at NIST and the other national metrology institutes, we want to make sure that our data is comparable and reproducible at other sites. And so we use both this instrument and the other to get that sort of complementary information. Now, in this case, I'm kind of showing here an example of moly disulfide because we're going to actually use that to calibrate the polarization data. I want to say what really led us to developing essentially a protocol. Again, this is a very sort of metrology-focused issue, is polarization information and data that's in publications is really all over the map. And we saw so many errors and challenging data that was presented that I thought it would be good to do. So in the National Metrology Institute community, we do these round robins or interlab studies, and we do those to validate protocols on how to do a measurement well. Often those how to do measurements are developed what are called documentary standards. And those are more used in an industrial setting, but these protocols actually give us lots of information and insight on obviously error analysis, reproducibility, and things of that nature. So that's what's taken place here. And while the main focus again was linear, you would be surprised how if you're not doing linear well, you really probably are not doing Helicity-Resolved Raman well either. And so it's a great place to kind of set context. So again, there's this protocol. It's on the archive, and we're finishing up some review to responses to reviewers. So we've selected a few different test materials. Ideally, when you select a test material, you want something that's readily available, everyone can buy, there's good reproducibility and things like that. So moly disulfide is a great sample for two reasons. It has two beautiful phonons of different symmetry within a very small window. Now, in this case, I'd like to say that in the protocol, or if you're kind of checking how well your polarization optics are working in your instrument, we highly recommend you not use few layer moly disulfide, but rather you use a freshly exfoliated bulk sample. That gives you the best reproducibility we've seen during the interlab study. Another great material, of course, is sapphire, the particular 001 cut, where there's a number of photons and phonons rather, and a beautiful a phonon there. And then silicon, of course, if you're a Raman person, you use silicon all the time to calibrate frequency. What is important, of course, is different cuts can give you different pieces of information, and so you want to be aware of the cut that you're using. And the TG, the T2 is an anisotropic response. It's an anisotropic response. And so it's different than the ones we've just talked about before that are tropic. And so that is important to that case. And most relevant, of course, this community is using quartz. And quartz does give you beautiful phonons, and you can purchase rather readily both the right and left-handed pieces of quartz. Of course, in the literature, there are lots of other material systems, and we have data on those as well. There are reasons that the quartz really is showing kind of stability and reproducibility that is required if you're doing a real sort of check of these sorts of things. So of course, so we have our two half wave plates. I'm just using the example here of having an edge filter. So we have two different half wave plates, and what they're doing, of course, is giving us two different angles. One angle that has to do with the incident Raman light, and then the angle between both the incident and the scattered light is the other angle. And what we're doing here is using the response of the A1G phonon to essentially establish our cross and parallel configuration. This is done after you've set your polarizers. There's a way to do that very well. I will say that using a polarimeter is really an important measurement tool. I know it is more expensive than some people wish to use. So I would, in the protocol, we have shared ways to get around not having a polarimeter, but being able to measure how elliptical your beam is will surprise you. So yeah, you definitely want to be aware of that. But what we're doing here is, as I mentioned, our ability to motorize those two half wave plates. What we can do is collect the data as a function, of course, of the whole rotation. And this allows us to set where parallel and perpendicular really are in the system. And then to set half wave plate one, either set it for the angular resolved linear setup, or we can jump to the half wave plate to do the Helicity-Resolved. The moly disulfide with a fifth objective showing you the effect of different wavelengths. And this is kind of becoming important as we're seeing in the quartz. I see I'm running out of time, so I'm going to have to jump ahead. But certainly if you have resonance effects, the wavelength selection really matters, and that can be problematic. Another quick thing that I do want to mention is an isotropic response versus an anisotropic response. What we were able to see rather quickly is in isotropic response, we see sort of beautiful response that matches with the theory, which is given here as we would expect. And here are examples of the other calibration samples. Now I just want to jump to the anisotropic response. So the theory shows us that the rotation of the two wave plates should give us these sorts of polar plots. This is actually the data that we collected, and we were quite troubled by that. And so we, of course, checked it numerous times. What we were able to see is that at specific angles, we got the theoretically expected values. However, at some angles, we saw disagreement with the theoretically predicted response of the T2G, again, the anisotropic. And what we found out very quickly that it was in fact the edge filter itself. That edge filter essentially is acting like a quarter wave plate in each wavelength. And therefore, each wavelength has a different correction that you would need to do to get rid of that effect. So it's just something for everyone to keep in mind as you are doing your polarization measurements. And this is just to show you in our home build instrument without that edge filter, we don't have this problem with either isotropic or anisotropic response. And then just quickly now, of course, I want to jump to the Helicity-Resolved measurements. Again, that polarimeter can really show you how your right and left-handedness is coming out of the objective. There are only a few material systems that can allow you to do that, so we highly suggest using the polarimeter because, of course, there are large regions that you're actually getting linear responses when you're using your quarter wave plate. Here is an example of, this is your typical Helicity-Resolved of 3 isotropic phonons in these 3 different samples. But now let's jump to the getting both the quarter wave plate and then the collection of the half wave plate where we can select the right or left-handedness within that linear scatter, which is what comes back from the sample. And here is an example of the chiral enantiomer of the quartz, the 2 quartzes, and here we have both silicon 111 and sapphire. And when you are using either right-left or left-right and comparing them, you see that the phonon position shifts oppositely in these 2 different measurements. And what's important here is using quartz, the resolution of your spectrometer is less important. Of course, there's the beautiful work on HGS and other samples. What we're seeing in the literature is some people are really, their instrument isn't able to resolve it, to spectrally resolve it. And so using quartz can give one better error, the better certainty for that value. I just wanted to show these are the various E phonons within the quartz, and you'll notice here you can get quite discernible values. And then lastly, I just want to say what we're seeing is that the circular intensity difference, the CID, really where you're using the combination of both the right-left and the left-right and getting that ratio is what we're seeing the strongest effect, the clearest way to characterize enantiomers in your sample. And here we're using the E2 mode of the quartz, and you can see this derivative-like function. It's very clear, and it's really absent in your sapphire and silicon. I apologize, I am running out of time, so I'm just going to quickly show you there is wavelength dependence to using quartz. I unfortunately don't have time to talk about it. Also, there is a temperature dependence. Many of us are doing temperature dependent measurements, and so these 2 things are very important and need to be kept in mind. So again, I thank you all for your attention, and I apologize I got over time. I'm happy to take a couple questions if anyone's left.